In last lecture, we have completed till chapter 5, that is application of first law of thermodynamics. In this lecture, uh, we will be starting our chapter 6. And this chapter 6 is second law of thermodynamics. Second law of thermodynamics. In last Q&A session, in Q&A session 3, at end, I think the question is incomplete. The last question which I was discussing earlier was incomplete due to some technical malfunction. The video is stopped at that point. I will try to cover that up in next Q&A session. After chapter 6 or chapter 7, I will see. I will create when I will create Q&A, I mean question session 4. I will cover that part up. Okay. So you needn't worry. And so we will start chapter 6, second law of thermodynamics. This second law of thermodynamics is also have other names like qualitative law, or we can also call it law of degradation of energy, or also call it directional law. Now, to understand how all of these names come into being, we should first know what is second law of thermodynamics. Okay, so when we studied the first law of thermodynamics, we simply said that total energy of a system is conserved. Okay, we said that net energy input is equal to energy stored plus energy output. Okay, so it does not provide any information regarding what direction of possible energy conversion is there. Okay, I mean we studied that a particular amount of heat is required to increase the temperature of the system or to provide a work. Okay, and after we provide certain work, it is possibility to get certain amount of heat, but it doesn't like inform us in which direction the possible energy conversion took place. So this is where second law of thermodynamics is required, and here second law of thermodynamics. So let me write something about it. So let me write it. Second law of thermodynamics provides the feasibility or direction of possible energy conversion. Possible energy conversion through the concept of entropy. And second law of thermodynamics provides the feasibility or direction of possible energy conversion through the concept of entropy, and also defines also defines concept of energy on quality basis. So this second law of thermodynamics defines the concept of energy on quality basis. From here, we know that heat is a low quality energy, and work is high quality energy, high grade energy, low grade energy. Okay, so that's why it is called, also called qualitative law, which we have mentioned here earlier. Okay, now it is the second law of thermodynamics, which is applied first in the numericals to find out direction, and after that we generally apply the first law of thermodynamics to find the value, how much heat is transferred or how much work is obtained. Okay, so the important point to note is heat is a, like I have mentioned earlier, heat is a low grade energy, and work is a high grade energy. Okay, so, and one more thing is necessary to tell you, that complete conversion of low grade energy to high grade is not possible. Like if I I want to convert heat into work, then complete conversion is not possible. Okay, but the complete conversion of high grade energy into low grade energy is possible. Okay, so you should remember this point also. Okay, next we will talk about what are thermal energy reservoir. Okay, okay, so before that, let me explain to you why it is called law of degradation of energy. So for this we should know the concept of entropy. So the energy of so let's wait for a few minutes, and I will discuss it again after I first discuss the concept of entropy. Then I will tell you why it is called law of degradation of energy. And the second and the last is directional law. So for directional law, as I said earlier, so the second law of thermodynamics provides the feasibility or direction of possible energy conversion. Hence, it is also called directional law. Okay. So let's start with thermal energy reservoir. Okay. So we will start with thermal energy Okay, so while discussing thermal energy reservoir, first we must know what is it is also denoted by TER. Okay, thermal energy reservoir. First, we must know what is thermal energy reservoir. Okay, so it is defined as a large body of infinite heat capacity. Okay, so thermal energy reservoir is defined as a large body of infinite capacity, and this which is capable of absorbing or rejecting an unlimited quantity of heat without suffering or without any appreciable change in thermodynamic condition. Okay, so thermal energy reservoir body is defined as the body with infinite heat capacity, and it is capable of absorbing or rejecting the unlimited quantity of heat without any appreciable change in thermodynamic condition. Okay, so basically there are two terms which will be frequently used in our further study. It is related to thermal energy reservoir only. So there are two types of thermal energy reservoir. First one is source, the second is sink. Okay, so let me tell you what is the source. The source is the, like, it can supply the infinite amount of energy. Okay, so it is a thermal energy reservoir which can supply infinite amount of heat without affecting its temperature. Okay, similarly, what is sink? Sink is also a thermal thermal energy reservoir body, and which can, like, for the source, it was a supplier of energy, but for the sink, which can absorb infinite amount of heat without affecting its temperature. Okay, so let's look at how source and sink are generally used. So let's consider an engine, engine E, which will provide us with some output. Let's say the engine E provides work W as the output, and it is further connected with two thermal energy reservoirs, uh, which are called source and another is called sink. Okay, so a heat is supplied from source to the engine, and engine performs some work and then rejects some heat to the sink. Okay, so the source is at higher temperature TH, and the sink is at lower temperature TL. Okay, so after this we are done with the thermal energy reservoir, and we will move to on. Next, we will look into some famous statements for second law of thermodynamics. There are two basically most famous statements. So we will talk about. Okay, so we will talk about the statements for second law of thermodynamics. So the first and famous statement is called Kelvin-Planck statement. Kelvin-Planck. Kelvin-Planck statement. Okay. So what does Kelvin-Planck statement represent? Let me write down its definition. So the Kelvin-Planck statement states that it is impossible to construct a device which operates in a cycle and produces work continuously while interacting with with single thermal reservoir. So the Kelvin-Plank statements represent tell us that it is impossible to create a or construct a device which can operate in a cyclic manner, producing work continuously while interacting with a single thermal reservoir. So let me show it in diagram form. So it is telling us that, let's say there is a device, and we cannot create such a device that can continuously provide some work W while interacting with a single thermal reservoir. Okay, let's say higher thermal reservoir. So it's saying that it is impossible. This process is impossible. Okay, so it means that to produce for a cyclic device to produce continuous work, it must interact with minimum of two reservoirs. Okay, one at the high temperature and one at low temperature. Okay, next we will see talk about the second. Okay, now one more thing before that. So if so this type of system which I have shown here, this is also called perpetual motion machine of second kind. So efficiency of a, let's write some definition here. One more line I will add. Perpetual motion machine of second kind is a heat engine having 100% efficiency, thermal efficiency, and is impossible according to Kelvin-Plank statement. Okay, so if we calculate the efficiency of this PMM2, so efficiency is desired effect upon heat input. So desired effect is W and heat input is Q, and from here we can say both are equal. So we will get it as 1, or we can also write it efficiency is equal to 100%. Okay, so for such a cycle where for ppm2 the efficiency of ppm2 is also, always 100%. Okay, next statement, the most famous statement is Clausius statement. Okay, so we will talk about the second statement. Clausius statement. So for Clausius statement, we will also write its definition. So it states that it is impossible to construct a device which operates in a cycle and transfers heat from low temperature reservoir to high temperature reservoir without consuming any other form of energy, that is work input equal to 0. So let me also represent it in diagrammatical way. So let's consider two thermal reservoir. This is at a high temperature TH and this is at lower temperature TL, and let's say this device absorbs heat QL from a low temperature and releases heat QH at a high temperature, and while doing this process the net heat there is no input, no other form of energy input required, at the work input is equal to 0. Okay, so it is Clausius statement tells us that such a device is impossible to make. Okay, impossible. Okay, for such a device, if we consider constructed the COP, which is again desired effect upon input. So desired effect here is your QH. If we consider heat engine, or if we consider refrigeration, so desired effect transfer heat from low temperature to high temperature is why without consuming. If we consider refrigeration, then the desired effect will be QL. So let's directly write it Q upon 0, which will be infinity. Okay, so such a device will have infinite COP, but such a device is impossible to make. Okay, so which device will be possible? Okay, so the question is, what kind of device can we make? They told that Kelvin-Plank told that a device, it is impossible to construct a device which operates in a cycle and produces work continuously while interacting with a single reservoir. He told this. Clausius again told that it is impossible to construct a device which operates in a cycle and transfers heat from low temperature reservoir to a high temperature reservoir without any other form of energy consumption. Okay, so but they didn't tell that what type of energy is possible. I mean, what type of device is possible to make. So for Clausius, Kelvin-Plank statement is basically for the heat for the engines, heat engines. Okay, for heat engines. So in case of heat engine, let me draw two devices here. First is heat engine. Second is three. Let me draw it three here. Second is heat pump, and third is refrigeration. Okay, so there will be, in all cases there will be two reservoirs. Having temperature TH, here it has a temperature TL, and let's just copy this diagram, and then we'll paste it both places. This will be included in all the diagrams. Okay, so we will just use it here. Okay, now we will add the additions which will be different for all the, like say this is heat engine. So heat engine will receive the heat QH from a high temperature reservoir, okay, QH, and reject some heat QL at a low temperature reservoir and produces a work W. Okay. Similarly, heat pump will absorb some heat QL from TL from lower temperature reservoir and rejects heat QH at a high temperature reservoir while taking some form of from work in form of electricity. Okay. And similarly, this also takes some refrigeration also take some heat from QL and delivers it to QH at TL and while taking some form of energy input. Okay. Now, what is difference between the heat engine, heat pump, and the main difference between heat pump and refrigeration, because they are almost same. Okay. First of all, if we talk about heat engine, then heat engine is a work producing device which takes low grade energy heat in form of input and produces high grade energy. Okay. So, but you can see here that it had taken the high grade energy and produced low grade energy, but there is some rejection. Okay. So from here we can say that the energy quantity of energy degraded. Okay, its quantity had decreased, but energy type grade is higher grade energy. Okay. Now if we talk about heat pump takes some high grade energy and transfers low grade energy from a low temperature to high temperature, similar to in case of refrigeration. Now difference is that in heat pump our desired effect is this QH. This QH is our desired effect. Okay. Similarly, in case of refrigeration, this QL, or you can also say that TL, is our desired effect. Okay. Next, we will be moving to coefficient of performance or energy performance ratio, and also we will discuss along with it what is efficiency. Okay. So let's discuss few terms, that is efficiency and COP. Okay. So efficiency is equal to output upon input. It can be also termed as work done net upon heat supplied. Also be termed as net heat upon heat supplied, because from first law we know that net work done in a cycle is equal to net work done in a cycle is equal to net heat supplied in a cycle. Okay. It can be also be written as, or heat supplied, we have used term QH earlier, so I can also use QH here. Okay. So, or Q net will be QH minus QL. Okay. That will be also equal to W net upon QH. This is efficiency again, and it can be also written in another form, that is 1 minus QL by QH. Okay. So these are few formats in which you can express the efficiency of the heat engine. And if you talk about the Kelvin scale, thermodynamic temperature scale or Kelvin scale, so we know that generally this Q from the heat released from the thermal reservoir, Q is directly proportional to temperature of the reservoir. Okay. It means that we can also write efficiency of the heat engine equal to 1 upon TL lower temperature upon TH higher temperature. Okay. And this is a very important relation. It is also known as Carnot efficiency. Okay. And indirectly used many times in many questions. We will see such questions next in our next question session. Okay. So next thing is COP. We have to consider also, we have already discussed what is efficiency. Okay. Next we have to consider COP. COP is also known as So let me write it first. What is this called? This is efficiency. This is also known as performance ratio. Okay, or we can also call it at performance, simply performance. What is the performance of engine? So performance of engine is defined by efficiency. Okay, now if we talk about heat pump or refrigeration, there if you calculate the efficiency, this term will came out to be what it will always be greater than 1. That is, it will be more, always be more than 100%. In general, if I tell you what is efficiency, so the first thing it will that will come, what is the value of efficiency if I ask you. So the first thing that will come into your mind is that it will be around 40%, 50%, 90%. At max it will be 100%. So due to this mentality, a term is new term is introduced, that is COP, coefficient of performance. COP, coefficient of performance, or we can also call it is EPR, energy performance ratio. Generally, COP or EPR values are always greater than 1. Okay, so it won't look odd to you. Okay, so this is also, COP is also a ratio of desired effect upon work input. Okay, so basically this was the desired output upon input. Here also this is output upon input. But where is the difference? Like here output was W net, here output is QH. Okay, if we talk about heat pump. Okay, let's talk about heat pump. Okay, so for heat pump, QH is our output, and here input was QH. Okay, but here input is, I mean, W that is supplied to the engine. Okay, W in, let's say W in. So I will write it here, W in. Okay, now we also know from the above cycle that from this cycle from here we can write it as like total energy QL supplied plus W in is equal to QH. So we can directly use it here. We can write it as QH is equal to QL plus W in. Okay, so using this we can write COP of heat pump is equal to QL plus W in upon W in. So COP of heat pump is equal to, we can write it as 1 plus QL by, okay, sorry, my mistake. I want to convert it not in terms of W input, because that is a variable. I want to convert it in terms of heat only. Okay, so QH will remain QH. From here we can calculate W in. Okay, and substitute here, that is QH minus QL. Okay, so this is a COP formula for heat pump. Similarly, if we talk about refrigeration, for refrigeration we can also write COP of refrigeration is equal to output upon input again, and here for refrigeration our output is not higher heat but lower heat amount, that is QL. Okay, by W input. Again, using the same relation, we can get COP of refrigeration is equal to QL upon QH minus QL. Okay, now something I have to mention, as I mentioned earlier, what here I mentioned that Q is directly proportional to T. Okay, in case of like if we consider Kelvin scale, so the Q is directly proportional to T. We know that Q is either MCP delta T or MCP delta T. So thermal reservoir is a body na. From that body, if we take out heat or provide heat, the change will be corresponding to T, proportional to T. So using Q is directly proportional to T, Q is directly proportional to T, we can write COP of heat pump is equal to TH upon TH minus TL. Okay, and COP of refrigeration is equal to TL upon TH minus TL. Okay, so these values are also known as Carnot COP. This is the maximum possible value of COP, and similarly if we talk about in terms of temperature, this is maximum possible value of efficiency for a given cycle. Okay, so you can say that for a real cycle the efficiency can never be 100%. Okay, the maximum efficiency is this will be the maximum efficiency possible. Okay, so similarly this is COP, these COP are also maximum coefficient of performance possible for a heat engine or a refrigeration. Okay, next since we have already defined COP of heat pump and COP of refrigeration, let's find the relation between both of them. Okay, so using the COP of refrigeration, we can like add 1 to both sides, like it is COP of refrigeration is equal to TL upon TH minus TL. Okay, we can add 1 on both sides, so what we will get, 1 plus COP of refrigeration is equal to TL plus TH minus TL upon TH minus TL. Okay, so from here we can get TH upon TH minus TL, and this term is exactly what is COP of heat pump is. Okay, so we can say that 1 plus COP of refrigeration is equal to COP of heat pump. Okay, this is also a important relation. Sometimes it is directly used in objective question. Okay, and yes, of course, this relation is only valid when when the temperature limit is same. Temperature limit is same for both heat pump and refrigeration. Okay, it's not like they both have different temperature limit and you directly apply this formula, then this will be incorrect. Okay, and we can also write from here you can see that efficiency is also TH minus TL upon TH. So you can also write, so let me write one more thing. Okay, so let's extend it some distance further, and now I will write one more thing here. Okay, so and this will be also be equal to 1 by efficiency of heat engine. Okay, now we are done with efficiencies and COPs. So I already told you all the relations that are possible, and if there is some difference in question, we can we will see while doing the questions. If there are some difference while doing question, like we can derive the new formulas if temperature is like not constant or varying and something else. So we will see many type of questions, and in those questions, from those questions we will learn more deeply about COP and efficiencies. Okay, so both heat, so you can see here that heat engine is a work producing device and heat pump and refrigeration are heat absorbing device. Sorry, work producing device and work absorbing device. Okay, so both, we can also say that both heat pump and refrigeration are known as the reverse heat engine. Why it is called reverse heat engine? Because it is directly opposite to that of heat engine operation. Okay. Okay, so we will move to next topic. Okay, so there are also these two statements for Kelvin-Planck statement and Clausius statement. So Kelvin-Planck statement tells that it is impossible for a heat engine to produce net work in a complete cycle if it exchanges heat only with bodies at a single fixed temperature. Okay, it means that it is impossible if a device interact only with a heat reservoir at a single temperature, like in this here I have drawn the figure, like I have mentioned that it was interacting with a single reservoir, and it was impossible to produce work continuously. Okay, now there are various other reservoirs also, but all are at same temperature. Since all are at same temperature, we can indicate them by single reservoir. Okay, let's say that there is another reservoir TH here, and that represent that transfer heat Q1, and this one represent transfer heat Q2. So we can combine both and tell that Q is equal to Q1 plus Q2. Okay. Similarly, in the case of Clausius statement, it is impossible to construct a device which operating in a cycle will produce no effect other than transfer of heat from the cooler to the hotter body. So it is impossible. If you want to transfer heat from cooler to hotter body, it will definitely produce effect other than the transfer of heat. Okay, like it will definitely require some work input. Okay, or some other type of effect, like we will study this also in refrigeration. There is a electrolysis refrigeration, which instead of requiring work input, it requires heat input also. Okay, so we will move to next topic, and our next topic is equivalence of Kelvin-Planck and Clausius statement. So what does equivalence of Kelvin-Planck statement and Clausius statement mean? It means that both Kelvin-Planck or Clausius tend to the same result. Okay, it means that let's drop it here. Okay, it means that that let's say at first glance, like we have seen earlier, so we see that both the Kelvin-Planck is for heat engines, and Clausius for work absorbing devices, and Kelvin-Planck for work producing devices. Okay, but if we delve deeper into both statements, we will find that both are two parallel statements of thermodynamics, of second law of thermodynamics. Okay, they both result give the same result. Okay, so for that we will how to verify this. So we will do two things. First, if we violate the Kelvin-Planck statement, we will see that our Clausius statement is automatically violated. And second, what we will do, we will try to violate the Clausius statement, and we will try to see if there is violation of Clausius statement, then Kelvin-Planck statement is feasible or not. Okay, we will see try these 2 points, and we can decide whether both are two parallel statements, or or not parallel. Okay, so let's start. So I will be drawing thermal reservoir. Let's wait for a minute. Okay, now for the equivalence of Kelvin-Planck and Clausius statement, we will first see how the violation of Kelvin-Planck statement result in the violation of Clausius statement, and violation of Clausius statement result in the violation of Kelvin-Planck statement. Okay, so let's consider in the first case, let's consider that a QH amount of heat is delivered from high thermal reservoir to the heat engine, okay, and the engine produces work W, and we will provide this work W, which will be equal to Q, okay, let's say it Q1, and we will provide this Q, this heat engine will take the heat Q1 from higher thermal reservoir and produce the work W, which will equal to Q1. Since there is no heat rejection, we have already said that Q2 or QL equal to 0 here. So this will represent the violation of Kelvin-Planck statement. So now we will see how it will affect our heat pump or refrigeration cycle. Okay, let's say this is a heat pump, and it will absorb the heat Q2 from a lower thermal reservoir, and then after absorbing this work or heat, it will release the heat Q1 plus Q2 back to the high thermal reservoir. Okay, so since we have already discussed that this heat engine will receive heat Q1 from a higher temperature reservoir, and after receiving the heat Q1, it will produce the equal amount of work, which will be Q1, and here it is a violation of Kelvin-Planck statement, and this work will be directly provided to a heat pump, which is attached between same temperature limit, and this heat pump will absorb the heat Q2 from lower temperature reservoir, and will send Q1 plus Q2 heat to higher temperature reservoir. So what will happen here, that we can see that this Q1 energy which it's sent to the higher reservoir will directly be transferred to the heat engine again. Okay, so this Q1 energy transferred here, but there is a Q2 energy which is further transmitted to TH, and it doesn't have any way to send it to you, so it will store this Q2 amount of heat. Okay, now we can see that we can reduce this figure as, let me redraw a new figure. So this temperature is, okay, so this temperature is TH, and we can this temperature reservoir is TL. So what is going on here is that we can see that this heat pump is connected to both TH and TL. Okay, heat pump is connected to TH and absorbing heat Q2, and is now constantly reducing. Now what is happening, that the heat engine which was attached is directly taking the heat Q1 from this heat pump only. So it is taking the heat Q1, and it is sending the heat Q2 to the reservoir, and this heat engine is again producing the work that is equal to Q1, and so this has become a loop. You can see here this has become a loop. So we can already consider this total as a cycle here. Okay, so consider this is a new device. Okay, so we can further reduce it in the form of TH and TL. It is absorbing heat Q2 from the low temperature reservoir and transferring heat Q2 to the same heat Q2 to the high temperature reservoir, and there is no other form of interaction with the surrounding. So it is requiring any form of energy. So we can clearly see here that due to the violation of Kelvin-Planck statement, it itself result in the violation of Clausius statement. Okay, so it is termed as, so it will be violation of Clausius statement statement. Okay, so now similarly we will see how the violation of Clausius statement affect the violation of Kelvin-Planck statement. Now let's consider that this refrigeration device is attached between TH and TL, and along with it heat engine is also attached. Okay, so this refrigerant device absorbs the heat Q from the low temperature and sent it to high temperature. Okay, so this is here is the without any form of work input, so work is equal to 0. Okay, is equal to 0. Okay, so for the 0 work input, it transmits the heat from a low temperature body to a high temperature body. This itself is a violation of Clausius law, which we are currently taking into consideration. Now assume that this heat engine is taking the heat Q from TH, the high temperature reservoir, and in turn it produces the provide heat Q dash to the low temperature reservoir and produces a work which is W. Okay, so what will happen here, that this heat which is refrigeration cycle has released to the high temperatures will directly be considered to be transferred to, I mean, this heat requirement can be directly I mean the heat input requirement for a heat engine can be directly compensated by a refrigeration output heat. Okay, that is this heat Q. So we can directly connect these 2 points, and it won't be requiring any high temperature. Okay, so we can now reduce it to, let me draw a new figure. So let's say this is TH. Okay, and let's say this is TL, and I can say that this is the refrigeration cycle. It is acquiring a heat Q from the low temperature, and in further release the heat Q after the cycle without any work input, and then this Q is directly transferred to heat engine. Okay, let me draw it first. Directly transferred to the heat engine. This Q is directly transferred to the heat engine without interacting with high temperature reservoir. Okay, and this heat engine will produce work W and will further provide the heat Q dash to the low temperature reservoir again. Now this whole system can be considered to have been made into a device. So let's say this is a new device which we can make, and this device, what will this device do? This device will interact with a single reservoir. Okay, let's wait for a minute. This device will require a single reservoir to make a device do continuous work while in interaction with a single reservoir at temperature TL, and which from here it will be receiving heat Q minus Q dash. Okay, so this itself is a violation of Kelvin-Planck statement. So from these two we can see that violation of Kelvin-Planck statement result in the violation of Clausius statement, and violation of Clausius statement will result in violation of Kelvin-Planck statement. Okay, this was the most important topic, I mean most important thing we have studied in equivalence of Kelvin-Planck and Clausius statement. This tells us that irrespective of their definitions, both tend to the same thing, both meaning of both definitions is the same, and both are the parallel statements of thermodynamics second law. Okay, now we will move to the next topic. So there are two more important points here which you should keep in mind about efficiency of reversible engine. So for reversible engine, if we consider refrigeration engine, so the efficiency of reversible engine between same temperature limits will be same. It means that eta reversible is a function of temperature limits only. Now there is one more point. The second point is efficiency of reversible cycle is independent of working fluid. Example, either it is argon, oxygen or nitrogen. For all the cycles, if the temperature limit is same, then the efficiency of reversible cycle between same temperature limits will be equal. Okay. Next we will talk about the thermodynamic temperature scale. Next we will discuss how to calculate the efficiency for multiple engine system. Okay, let's say that let me draw a diagram first. So let's say that there is a energy reservoir temperature T1, which is from which engine E1 is interacting, and it is further interacting with another reservoir with temperature T2. Let's say this is a reservoir with temperature T2, and this T2 is being shared by another engine E2, and which in turns interact with next reservoir, that is at T3. Okay, so let's say that Q1 amount of heat is received from T1. E1 receives Q1 amount of heat from T1 and produces the work W1 after releasing the heat Q2 to the reservoir at its temperature T2, and this Q2 will be supplied or absorbed by the engine E2, which in turn produces work W2 and rejects heat Q3 to the T3 reservoir. Okay, now assuming that all the cycles are what the all cycles are? All cycles are reversible. Let's say that engine E1 and E2 are reversible, so we can consider that this complete system combined E1 E2 with along with the reservoir T2 to another engine E3, and if so, here we can say that if E1 and E2 are reversible, then it would mean that E3 is also reversible. Okay, so we can write the equations for efficiency of at 1 is equal to 1 minus Q2 by Q1. Efficiency of engine 2 is equal to 1 minus Q3 by Q2, and efficiency for engine 3 can be written as, if we assume the completed engine 3, we can write it as 1 minus Q3 by Q1, which can be further written as 1 minus Q3 by Q2 into Q2 by Q1. Okay, now from these two equations we can see that Q2 by Q1 is equal to 1 minus efficiency 1, and Q3 by Q2 is equal to 1 minus efficiency 2. So the overall efficiency of engine 3 can be written as can be written as 1 minus Q2 by Q3 by Q2. Q3 by Q2 is represented by 1 minus efficiency 2 into 1 minus efficiency 1. So from this we can also write it as N3 is equal to, if we multiply the brackets and further explorate it, we can write it as eta 1 plus eta 2 minus eta 1 eta 2. But from this expression we can write a very general equation for nth state system. So efficiency of if there are many engines attached in series, so we can write efficiency is equal to 1 minus eta 1 into 1 minus eta 2 into 1 minus eta 3, and in similar way we can proceed it. Okay, so this will be all for today, and in next class we will be discussing the Clausius inequality, and further we will discuss about concept of entropy and everything. Thank you for today.